Welcome to True Projects. In this video, we are going to explain about the project title, a novel method for brain tumor detection using multi-wavelet transform. Before diving into the execution, let me give you an overview of the project. Let us first understand what brain tumor is. A brain tumor is an abnormal growth of cells in the brain, either benign, non-cancerous, or malignant cancerous. Benign tumors grow slowly and stay localized, while malignant tumors are aggressive and can spread. Symptoms vary, including headaches and seizures. Diagnosis involves imaging tests and biopsy with treatments like surgery, radiation, and chemotherapy. Prognosis varies based on tumor type and treatment response, with ongoing monitoring needed. The aim of the project is to enhance brain tumor detection using multi-wavelet transform MWT, aiming for improved accuracy and efficiency in early detection. Traditional methods for brain tumor detection include CT, computed tomography scans, MRI, magnetic resonance imaging, clinical assessment, biopsy, PET, and EEG are crucial for diagnosing tumors and guiding treatment. However, these traditional methods have some limitations in sensitivity, subjectivity, cost, resolution, and functional correlation, underscoring the need for improved approaches to enhance accuracy and accessibility in diagnosis. In the base paper, to overcome the limitations of traditional methods, the author has proposed multi-wavelet transform with advanced machine learning techniques like convolutional neural network for precise brain tumor detection. Multi-wavelet transform enhances feature extraction from brain images, aiding in precise classification of tumors, which can facilitate early diagnosis and better patient outcomes. To further improve performance, we have proposed convolutional neural network and exception models for classification. These advanced techniques aim to enhance accuracy and efficiency in brain tumor detection. In the project, we classified fused MRI and CT brain images into two classes: normal, indicating the absence of brain tumor, and abnormal, indicating the presence of brain tumor. The classification is based on the analysis of the combined MRI and CT images. The beneficiaries of the project include patients, healthcare professionals, medical researchers, healthcare systems, and society at large, benefiting from improved brain tumor detection, precise diagnostics, advanced research, optimized resource allocation, and enhanced healthcare outcomes. To implement this project, we need software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Algorithms used. These are the algorithms which we have used in the project. The first algorithm is proposed in the base paper, and these are the algorithms which we have proposed to further improve the performance for detecting brain tumor. Out of these algorithms, exception outperformed others, and that is the reason we have deployed it in the Flask. Let me explain you what exception is. Exception is a special kind of deep learning technique. It's known for being good at understanding images. It does this by breaking down the process of looking at images into two steps. First, it looks at different parts of the image separately. This is called depthwise convolution. Then it combines these parts to understand how they relate to each other. This is called point-wise convolution. This helps exception to understand images better and pick up on important details. One of its strengths is that it's really efficient at doing this, which is important when we are dealing with lots of images, like in medical analysis. Plus, it's great at figuring out what features in the images are important for making classifications. Another important thing about exception is that it can learn from other data sets before being used for specific tasks. That is transfer learning. This makes it super adaptable and useful for projects like detecting brain tumor from medical images. Now let us execute the project. To execute the project, we need to open the code folder, which contains the project source code files. And now we will discuss each of the folder in detail. This is the CT folder, that is computed tomography folder. In this project, we have utilized brain tumor MRI and CT data. This is the CT data, which is having two subfolders, namely no and yes, which contains images of CT scans of brain. In the no folder, we have CT images that do not show any signs of brain tumor. These are normal brain CT scans. And in the yes folder, we have CT images that depict the presence of a brain tumor. These images show abnormal growth of masses within the brain tissue, indicating the presence of a tumor. This is the fused image folder. In this, we have fused CT and MRI images using wavelet transform method. In this folder, we again have two subfolders, namely no and yes. In the no folder, we have the fused images of CT and MRI brain scans, which are normal, which do not show any presence of brain tumor. And in the yes folder, we have the fused images, which show the presence of a tumor. This is the MRI data, that is magnetic resonance imaging. In this folder, we again have two subfolders which contains images of MRI scans of brain. In the no folder, we have MRI images that do not show any signs of a brain tumor. These are normal brain MRI scans. And in the yes folder, we have MRI images that depict the presence of a brain tumor. These images show abnormal growth or masses within the brain tissue, indicating the presence of a tumor. We have split the fused images, both yes and no images, into train and test sets. And these are stored in the output folder. So here we have train and validation folders, which contains both no and yes images from the fused images folder. So in the train folder, again, we have no and yes. In the no folder, we have the images which do not contain the brain tumor. And in the yes folder, we have the images which contains the brain tumor. So these images are used to train the models. And in the validation folder, again, we have no and yes folder. In the no folder, we have the images which do not contain brain tumor. And in the yes folder, we have the images which contains the brain tumor. And these images are used to test the performance. This is the sample folder, in which we have again two subfolders, no and yes. In the no folder, we have the images which do not depict brain tumor. And in the yes folder, we have the images which has brain tumor. These images will be used during the execution. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally. At the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register, but I have already registered. So click on login here. So here we need to enter the username and the password, which are static, and then click on login. We have logged in successfully and we are redirected to the prediction page. So here we need to upload the fused MRI and CT brain images, and after uploading the image, the application will predict whether brain tumor is detected or not. Click on choose file to select the image. So here from the sample dataset, I'm selecting this image. So here we can see that the image is uploaded. Now click on upload button. This is the uploaded image and it is predicted as normal. There is no brain tumor on fused MRI and CT brain image. It means that the person is not having the brain tumor. Now click on try again. Let us upload some more images. Click on choose file. So here from the sample data set, I am selecting this image. Now click on upload button. This is the uploaded image and it is predicted as abnormal. There is brain tumor on fused MRI and CT brain image. It means that the person is having the brain tumor. Click on try again. Let us upload some more images. I'm selecting this image. Now click on upload button. So this is the uploaded image and it is predicted as abnormal. There is brain tumor on fused MRI and CT brain image. It means that the person is having the brain tumor based on the CT and MRI fused brain image. Let us upload some more images. So here I'm selecting this image from the sample data set. So this is the uploaded image and it is predicted as normal. There is no brain tumor on fused MRI and CT brain image. It means that the person is not having the brain tumor based on the fused MRI and CT scan image. Let us upload some more images. Click on try again. This time we will upload the image from the train set itself. So I'm uploading this image. Click on upload button. This is the uploaded image and it is predicted as normal. There is no brain tumor on fused MRI and CT brain image. Let us upload some more images. Click on choose file. This is the image which I am uploading. So here, this is the uploaded image and it is predicted as normal. There is no brain tumor on fused MRI and CT brain image. Let us upload some more images. Click on choose file. Let us upload the images from the validation set. So here, this is the image. Click on upload button. This is the uploaded image and it is predicted as normal. There is no brain tumor on fused MRI and CT brain image. It means that the person is not having the brain tumor based on the fused MRI and CT brain image. In this way, just by uploading the fused CT and MRI images, we can predict whether brain tumor is detected or not. That is whether it is normal or abnormal. Now click on graph link here. So here we have the loss and accuracy curve of exception. So this is the loss curve of exception. For every increasing epoch, loss is decreasing in both training and validation. And for every increasing epoch, accuracy is increasing in both training and validation, which means model is performing well. And here we have the comparison graphs for the different evaluation metrics: accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of how well a model correctly predicts outcomes. It represents the proportion of correctly classified instances among all instances evaluated. This is the precision comparison graph. Here on the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a measure of the correctness of positive predictions made by a classifier. This is the recall comparison graph. Here on the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall is a measure of the classifier's ability to correctly identify all relevant instances from a data set. This is FN comparison graph. Here on the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score combines precision and recall into a single value. It provides a balance between precision and recall, taking into account both false positives and false negatives. The algorithm which is performing well will be used for prediction. Now click on sign out link. So we have built a system that predicts whether brain tumor is normal or abnormal using the fused CT and MRI brain images. We observed that exception outperformed others, and we have deployed it in the Flask.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.